Hey everyone, today we are looking at something called logarithmic differentiation. So just to back up for a moment, so we've done derivatives like y equals x cubed, no big deal, right? Y prime equals 3x squared. We've also done things like y equals 3 to the x, where y prime is 3 to the x natural log 3. But what we haven't done is something like this, y equals x to the power of x. You probably haven't even seen a graph of that. If you try that on your calculator, it doesn't graph very well. Just letting you know. So which rule would you follow? Do you use the power rule where you subtract 1 from the exponent and bring the original exponent down in front? So you're like, oh, well, y prime would be x times x to the n minus 1, which actually would be, if you use a rule of exponent on that, you would get x to the n again. Oops, I shouldn't have said n minus 1. I should have said x minus 1. So it's like, is that what you do? Or do you do the same rule as what we do on 3 to the x, where you would have y prime equals 3 to the, oops, not 3. I was looking above it. X to the x times natural log x. And the answer to that is no, actually, you don't do either of those things. They're both totally wrong. It's unfortunate, isn't it? Because if you think about it, like having to math is patterns, right? And so it's like, I'm following a pattern. I followed the same pattern as the power rule, or I followed the same pattern as the b to the x rule. Well, you shouldn't have choices to make with respect to patterns. That's not how patterns typically work in math. Both of these are wrong. What we have to do is something called logarithmic differentiation. And that's gonna, it's a pretty challenging thing for a lot of people. So we take our y equals x to the x, and we take the natural log of both sides. So we have natural log of y equals the natural log of x to the x. Just a reminder, when you see natural log of when you have an exponent like that, like a natural log of a to the b, remember that that's b times natural log a. This is the whole reason we're doing this, is actually because it makes that exponent not an exponent anymore. So we have natural log of y equals x times the natural log of x. Now we have to think back a ways. Do you remember doing that implicit differentiation, which is when we had our x's and y's all mixed together and we would derive and then we would solve for dy dx? Yeah, we're going to do that here. So the derivative of natural log y is 1 over y, and then the chain rule, right? So we have, just switching colors here. So we have 1 over y times, remember, think about that as an inside. So the derivative of the outside is the 1 over. Keep the inside the same, the y, times derivative of the inside. The derivative of y is y prime, or dy dx. I like dy dx just because it's a little more visible and I'm less likely to lose it. Okay, on the right side, we have to use the product rule on that. Remember our product rule that if you have like the derivative of u times v, u prime v plus uv prime. Remember that way back when? So where u in this case is x, so u prime is 1, v is natural log x, v prime is 1 over x. You're going to be using the product rule a ton. You're also going to be using the chain rule a ton. We're always using the chain rule derivatives, right? Okay, so derivative of the first is 1 times the second natural log x, plus the first, which is x, times derivative of the second, which is 1 over x. And now we're going to solve for dy dx. So we have dy dx is natural log of x plus, I'm going to clean that up, 1 times y. But then we want this is a function. We want this as a function as well. So instead of writing a y, we're going to swap it for what y is equal to. So dy dx is natural log of x plus 1 times y, which is really x to the x. And that is our answer. So again, we take the natural log of both sides of the equation. We use that log rule to bring that exponent down. And then we use that implicit differentiation. Think way back, look it up if you need to, implicit differentiation. So you can go back to the video on that if you need. So that implicit differentiation right there, and then solving for dy dx. And then once you've solved for dy dx, replace y for what y is equal to. So I'm going to add a little, so solve for dy dx, and then last step is to replace y with what it's equal to. So let's look at another example. Oh dear, I was a little off the screen there. I'll let you look at that for a sec while I write down our next example. So we have, okay, so second example here, we have y equals sine x to the cosine x. So my first step, I'm going to take the natural log of both sides. So I have natural log y equals the natural log of sine x to the cosine x. And then I can bring my exponent down. So I have natural log y equals cosine x times the natural log of sine x. I know some of y'all will go straight to the second line here, the second green line, and that's totally fine. It's a reasonable amount to skip. Like when you're like, I know I'm taking the natural log of both sides, I'm going to throw that cosine x down in front. That's totally fine. So we do that. Then we derive both sides, so we can get, so on the left we get 1 over y times dy dx. You're going to have that just like practically in your muscle memory because you're going to do it so often. And then once again we have to product rule this, so I'm going to go ahead and write down my u is cosine x, my u prime is negative sine x, v is natural log sine x, v prime is 1 over sine x, and then remember chain rule, so cosine x. And then I'm going to clean that up because I would prefer to write less than more. Remember that cosine x divided by sine x is cotangent x. So we have our derivative of the left side and then product ruling on the right. So derivative of the first, we get negative sine x times the second, natural log sine x, plus the first, which is cosine x, times derivative of the second, which was that cotangent x. And then we solve for dy dx. So dy dx is that negative sine x times natural log sine x plus cosine x times cotangent x. Throw that guy in parentheses. Be really careful about that. I didn't emphasize that the last time. And then multiplying that times y. And a lot of times many of you are going to do this. You'll be like, instead of just writing a times y here and then writing this whole line again, you would just go straight to like, oh, times y. But y really is that sine x times sine x to the cosine x. I'm going to do that too. And since I accidentally made a bit of a space, I'm going to make sure that multiplication dot is very visible. So there's our second example. We'll do one more example. And this example, I will tell you, it is spicy. Like, it's going to make your teeth hurt or your nose run or something. It is a spicy one because it's actually going to use a couple of log rules. And this is a problem that, like, you definitely could not do without, actually any of these so far you couldn't do without logarithmic differentiation. So if we have y equals, it's going to be a fraction. This is going to be ugly. Brace yourself. Cosine of x to the power of x squared divided by tangent of x to the power of e to the x. So, by the way, there are times that you can do logarithmic differentiation just for the purpose of using log rules to break something down. Because what would you rather do, like a really complicated like product and quotient rule, or a series of smaller things? So it can be a good strategy to use, and you'll do that on the assignment once. I threw one in there just to prove a point. Okay, so just a reminder, if you have the natural log of a over b, because when we take the natural log of both sides, we're going to have a fraction here. That's natural log of a minus natural log of b. And that's one of the rules. And we'll also use the fact that the exponent comes down. So taking the natural log of both sides, and some of y'all will probably just like smoosh a natural log into here. I'm not doing that just so we can have a nice clear view of our original equation. So natural log y equals natural log of, brace yourself, ugly thing, cosine x to the x squared over tangent x to the e to the x. So using log rules on this, I'm going to use both the subtraction and the exponent at once because I feel like going a little nuts here. So remember that x squared is going to come to the front. I'll have basically it's looking at natural log of the cosine x squared. So I can move the x squared down. So I have x squared, natural log of cosine x, and then minus that e to the x can come down. So e to the x times the natural log of tangent x. So this breaks it down to more manageable pieces. And yes, we'll have to product rule and chain rule, but it's all good. We can do this. So on the left, we'll have that 1 over y, so derivative of the outside, keep the inside the same, times derivative of the inside is our dy dx. And then I'm not going to write my u and v down. I'm just going to, maybe I will. Do I want to do this? Yeah, I think I do. So I'm going to throw this over here. So for this first guy, I have a u is x squared, u prime is 2x, v is natural log of cosine x, v prime is 1 over cosine x times negative sine x. So that's a negative tangent x. And then I'll write the second part in a moment. I'm just going to use that. So I have derivative of the first, the 2x, times the second, natural log of cosine x, plus the first, the x squared, times derivative of the second, which is that negative tangent x. And then be a little careful here, and it might help if you throw this guy like into parentheses here, just as a reminder, like here's the derivative of the first piece of it, and then minus, I'll throw a big parenthesis down and I'll do the derivative of the second part. So for this second part, I have, where am I going to put this? I'm going to come down. This is a little ugly. I didn't plan very well. U is e to the x, u prime is e to the x, v is natural log tangent x, and v prime is 1 over tangent x times derivative of the inside is secant squared x. To make that a little tidier, remember 1 over tangent x is cotangent x, so cotangent x secant squared x, just for the sake of slightly more tidy. Okay, so u prime, e to the x, times v, which is the natural log of tangent x, plus u, which is e to the x, times derivative of, or times the v prime, which is the cotangent x secant squared x. So in the second set of parentheses is the derivative of the e to the x natural log tangent x. You have to really watch things like your parentheses. Notice, because I'm subtracting all of that. So really be careful of that, because that's a very common mistake. So throwing parentheses around things is a nice way to kind of just keep yourself organized. Okay, now we need to solve for dy dx, and just so I have room to write, because this is going to be long, I'm going to have to skip a little space. That's fine. Sometimes planning ahead's overrated, right? Actually, I really like planning ahead. Okay, so dy dx is, I do need a parenthesis. You'll see why in a moment. So 2x natural log of cosine x minus, I'm going to clean that up a little bit, x squared tangent x. And then I have minus e to the x natural log tangent x, and then minus that second piece, so minus e to the x cotangent x secant squared x. And then this whole thing is in parentheses, and that whole thing gets multiplied by y. Rather than writing times y and then like having to write this whole thing again, I'm going to go ahead and grab my original. So my times y here is times this cosine x to the x squared over tangent x to the e to the x. So this question is about as spicy as they come. So just if you keep yourself organized, make the notes of your u and u prime, v prime if you need to, just to kind of keep yourself organized. And then that line actually goes down to there. And try to plan your space. It helps. Or just have scratch paper handy maybe for things like the u's and u primes. But if you can do this problem, you know that you have this stuff nailed pretty solidly. So that is logarithmic differentiation, and I apologize for the length of this video.